Stuff that's working anyway. I don't know how good it is. We will want to check out some stuff in world class today, but let's kind of warm up together first, just a little bit. I created a Jupyter notebook that I think will help those who have no programming experience, and maybe those who do just learn a couple cool things that are mathy in Python that you haven't ever had to do before. Maybe not, but we'll take a look at that all in a minute. So I think that our main book for this course is going to be the Intuitive Guide to Numerical Methods, and that is in the content area. It's a great book. It's really well written, and I would actually like you to read something for next Monday. If you could please read up through rates of convergence after today, and a lot of it will make sense after today. Today we're going to do some business, and then there's just this thing that I saw out of the corner of my eye. I saw like a shiny thing in a tree, and I flew over, and I'm like a crow. I guess that's what I'm saying. So I saw cool math that we have to talk about. And it's totally related to what we're doing. So read up through rates of convergence. That's just chapter 1. We'll talk a little bit about that today. So the problem at hand, our first problem at hand, is solving equations. And this, I'm gonna actually write this a couple of ways. Solving equations is equivalent to finding roots. So if you see any of these phrases about, they're all the same thing. Finding zeros. However you spell zeros. I don't know. There might be an E in there. Is there an E in it? Is there an E in zeros? I can't spell that word, or heroes.
Heroes has an E.
Heroes has an E?
That looks right.
Yeah, you know what I mean. So, yeah, we're good. Good to go. So, in other words, solve the problem, find, I'm going to put all in parentheses because it's not always the case, but find all solutions to f of x equals 0 for some function f. And right now, I'm not putting any restrictions on f. We don't know its domain. We don't know if it's continuous or discontinuous or differentiable or any of those things, and we'll have to make assumptions depending on the method there we go, thank you. The method we are looking at. So let's draw a picture to talk about what we are to see what we're thinking here. So I've got a graph of x. And what I'm looking for when I find f of x equals 0 are these things right here. So these intercepts of the x-axis, those are our solutions. And for this one, this would be all the solutions, because if it goes on like it's indicating, it never intersects the x-axis again. So this is our main problem. We're going to spend about a week or so looking at these methods. Has anybody ever done any stuff with this before? Okay, good, all right. Can you see okay there, Lavina? Yeah, all right.
Very comfortable with myself.
Okay. So we're going to kind of focus on just one problem today that I think is fun and intuitive, and I cannot like seriously, bro. I need to get the wallet chain. That's a really good idea. Okay. Now I have a mission in life. Just a little chain with a clip, right? Nice. Never lose it again.
Just buy a magnet.
Buy a magnet. Oh, a magnetic one of these?
Or just put a magnet and glue it on top of it.
I'll get some of those like super rare earth ones and like never be able to get it off again. Crush my fingers. Oh. Anyway, sorry. I'm a little punchy today because I had to deal with some irritating people yesterday. So, whatever sense that makes. So a specific example that we're going to run through for the rest of the day. I'm going to write it in a really interesting way. Find the square root of 3. How much of that do you know just off the top of your head? Like just square root of 3? We'll keep it up here because we're going to do some approximations. What do we know about it? What's the first digit? That's good. Because it's between the square root of 1 and the square root of 4. So that first digit needs to be a 1. Anybody got anything else for me? Pretty good. That's about all I remembered. I think it's 050 next, but I'm not going to say it. So that's an irrational number. This goes on forever and ever. We'll never have full precision beyond the symbol that represents full precision. But we're not interested in that. We want to do this on a computer. On a computer is the unspoken for each of these. So how do I convert that? How could I convert that into a problem of our form? Solve f of x equals 0. What f would give me that as a solution? X squared minus 3, check it out. So let's let f of x equal x squared minus 3, and then the roots of that are going to be square root of 3 and negative square root of 3. So this actually gives more than we're looking for. I always recommend getting a graph for lots of reasons. You'll see why as we progress. But if I graph y equals x squared minus 3, get this lovely parabola, and I see that those intercepts are the things I'm looking for. So one of the things that we'll have to be careful for in this method is making sure we're finding the one we want. Making sure we're finding that positive root, not the negative root. And this first method that we're going to look at is very simple, very intuitive. And it would probably be like if we just had to sit around and brainstorm how to do this, this might be the first thing we came up with. So let's look at our first method. It's called the bisection method. Lovely and intuitive and just cutting shit in half forever and ever, and then eventually stopping, which is not forever, I guess. But doing it for a long time. So here's our idea, our plan, or our idea. We're going to, first off, and let's kind of just focus in over here. Let's just focus on this side. So step 1 is find a bracket for our solution. And what I mean by a bracket is just a range of x values that I'm pretty sure it's between. So I want to initialize this process by saying, square root of 3. Well, okay, it's probably between 0 and something else. We're pretty sure it's under the square root of 4, so we could say 0 to 2 would be a pretty reasonable thing. This is all making sense? See where I'm going with this? Might not see where I'm going with it. See where we've been? Cool. So that's my initial bracket. Just call it I sub 0. I'm not sure. I might use that notation in just a little bit. All right, so what's important about this bracket is that I can discern there's a root in between here because the function is negative at 0 and positive at 2. So note that if f of x is x squared minus 3, and that's what I'm using here, that f of 0 is negative 3, and f of 2 is positive 1. So there's a sign change here. Well, let's get this. This thing is really just ridiculous, useless, absolute crap, unbelievable. Is that enough bad stuff to say about it? Okay. Does that screw you over?
No, I'm good.
Okay, thanks. You're a trooper, though. You might not say. So here we have a sign change. So f of x star must equal 0 for some, and I'm going to call on a calc result, but you have to tell me why I can make this conclusion. A sign change so that f of x star equals 0 for some x star in the open interval 0 to 2. So now that's open. So somebody help me out here. Well, how do I know that? I can look, besides, we don't want to look at the picture. What tells me that? And what assumptions do I need to make? Yeah, Ava.
Because one of them is negative and one is positive, so we know that it change at some point.
What can you think of the calc result? Because let me show you something here. Let me just confound this a little bit as I lost that fucking nice tiny board. I need to erase a lot. All right, let's just kind of put it right there and never get. Oh, that's actually not bad. Okay, cool. So, like, yeah. Where were you?
Oh, you hung the eraser.
Yeah, I did. Bad eraser. Put them in the stocks. So, what about this one, Ava? So I'm gonna do a different function on 0 to 2 that looks like this. So f of x is 1 if x is greater than or equal to 1, and it's equal to -1 if x is less than 1. So I've got a piecewise function here. Up until x equals 1, it spits out a -1. And then it looks like it jumps. It can never actually get to 1 on that side. We pick it up on the other, and we have that. So now that function, notice here, let's call this f bogus. Notice that f bogus at 0 is negative, and f bogus at 2 is positive. So that also has that same property of a sign change, but it doesn't, there's no 0, there's no solution. It never equals 0. What do I need to assume?
The function's continuous.
We need continuity. So I have to assume that f is continuous for this to work. What is the calc result that says if I have a continuous function that takes on this value and this value, it takes on all values in between? What's that?
Integral?
Not integral. No, it's like something theorem or yeah.
The intermediate value.
Intermediate value theorem. Intermediate value theorem says that if you have a function that at some point is this, and it's continuous, then look at the output, the final output value. It will take on every value between its beginning value and its ending value. And if it doesn't, it would have had to jump over those. So continuity ensures that. So we assume f is continuous. We don't need anything else for this method. We don't need differentiable. What would differentiable mean, picture-wise? What does a differentiable function look like picture-wise? Is this differentiable? Sorry.
What did you drop?
Yeah, what did I drop? Exactly, what did I drop? Oh, I just want to knock this thing over.
You should just take it out of the room, put it in the hall.
Can I?
Maybe.
Probably like plug in the cord.
It's, the cords are taped down.
Punch the plug in.
It's kind of alive.
I think this was the only one that was actually.
No,
There's a power cord. What if we shove it over there? Maybe that could do it. Oh, there. There.
Oh.
Ah. Okay, cool, much better. Is that continuous? Continuous, is it differentiable? Why not, Thomas? Yeah.
Because it has a sharp corner.
Absolutely. So the sharp corner says it's not differentiable. Let's just talk really quick, because this class isn't just about learning some algorithms and typing them in and watching them roll. We're going to do a bunch of math. You're gonna learn a lot or refresh a lot of math along the way. Not differentiable here. Differentiability is about the tangent lines. If the tangent lines to the curve from the left side smoothly coalesce into the ones from the right side, that's differentiable. So it's actually kind of a continuous derivative in a way that gives me differentiability. We'll get to that. We'll need that on our next method, but not yet. And there you are. Right where I said you'd be. Okay, so step one is get that bracket, and we need to have f continuous. So step two is going to be, I kind of wish I'd written it over there, but step two is find the midpoint of our initial interval, our initial bracket. And let's call that probably C. So C equals midpoint. I'm going to write this out in a generic way of initial bracket. And let's call it AB in general so that we can start getting this more generic. For us, it was 0, 3. So for us, C is equal to, where was the midpoint? 1. Yeah, because I use 0 and 2. So C equals, and it's, look here, C is just going to be 1/2 B minus A. B plus A, the average of those two. So down here, our AB equaled 0, 2. We know that we should proceed because we have a continuous function and it changes sign on this interval. If it didn't change sign, we would just end and say, function doesn't have a root on this interval. We'll talk about that in a minute too. So, here's our halfway point. C is 1/2, 0 plus 2, we get 1. And let me draw my function out again, like that. And there's the prize, square root of 3. And here's the midpoint 1. Suggestions on maybe what to do next?
Like you turn your bracket into 1 and then 2?
Yeah, beautiful. So why did you pick 1 to 2, Josephine? That's perfect. Why did you pick this one over this one?
Because that's where the root is.
Yes, but how could we tell? Yes, how would I know? How would a computer know where the root is? You're right. So how would the computer know? Because you can see it, right? How does the computer know that the root lives here versus over here? Think back to the beginning. What was that initial condition we needed?
Like just for the specific case?
Just for
Because,
this specific case, yeah.
Square root of 3 is in between square root of 1 and square root of 4?
Yes, yes, but what if I had, so going back to it, we needed that sign change. That's what I'm trying to get at. You're probably like thinking, what the hell is he trying to get me to? So you intuitively knew that, and also you can see it, but intuitively, we've got two choices. We've got this half or this half. We're always going to pick the half where there's a sign change. So choose the half where the sign changes again. And honestly, this is about it. Repeat, make a new bracket using that. So let's actually write up the next step. Why didn't I hang him back up? Oh, he actually does sit there. I can actually do this in a less foolish way. Except that foolish is fun. So, we will make 1, 2 our next bracket. Because f of 1 is negative and f of 2 is positive. And I want to show you kind of a different way to think of this that you're going to see in the code, i.e. f of the left endpoint times f of the right endpoint is negative. That says they have to be opposite signs, so that's how we'll test in code if we actually have a sign change. Okay, all good? Yeah, cool. So repeat with 1, 2 as new bracket. Oh, I already said that. We'll make 1, 2 our next second. So now find the midpoint of 1, 2, and that's going to be C equals 3/2, aka 1.5. And we come over here and let's look at this again. So I'm going to put my square. This is the last one I'm going to do. So if this is killing you, just hold on a second. There's 2. There's 0. Here was our first bracket 1. Our first bracket, initializing bracket, was that. And we moved here, and now we've got. I kind of didn't draw that great, did I? Because I know that 1.7 is on the right side. So, and then there's 1.5. Find the midpoint there, and then repeat. So since f of 1.5 times f of 2 is less than 0, new bracket equals 1.52. And we continue, and we will never have a number. We're never going to get a single number out that says this is the root. We're going to get a range. We're going to get a left endpoint. It's between this thing and this thing. So our goal is to get this thing as small as possible. We want to close in on the root. So that means we're going to run this method until that interval is less than a tolerance level long. So let's do some pseudocode. Pseudocode is just not meant to be typed into a computer. If you're a CS person, you write pseudocode as kind of a first draft, but it's just to get the flow. So we're going to assume some things here. We're going to assume that f of x is continuous where it matters. Doesn't have to be continuous everywhere as long as we're pretty sure it's continuous where we're looking. We're going to initialize. And to initialize, we're going to set a equal to the left bracket value. We're going to set b equal to the right bracket value. We're going to do this all in the code. And then we're going to start rolling. So the first thing we want to do is check that we should even go further. So initial check is f of a times, and I'm going to use the CS, the computer form of times here. That's not convolution or any weird mathing. I'm just timesing is less than 0. If not, print no root. And then we'll just print out the details. And we'll let the user have a little bit of deets about what is actually happening here. So if that is not the case, else that means we do have a root in there, and now we're going to begin our routine. Folks who haven't done any programming, does this language feel natural to you? If this is the case, do this, else do this. Hard to say? Like, literally everyone's just looking at me with no feedback. So I'm going to turn away and pretend that this is okay. All right, else begin the main algorithm. And so the main algorithm is going to be a loop. And we're going to talk together about what we want to be in this loop. And we might come back and tweak a few initial assumptions. So we're going to loop, and I'm just gonna write loop here, so we don't have to introduce variables or anything. Loop, and we're gonna do this while our tolerance, well, let's hold off on that. We'll come on our condition we're gonna loop over in a minute. So the first thing we're gonna do is crank out the halfway point of our current interval. And make a little, I'm gonna make comments over here. This is the midpoint of current bracket. And then we're gonna test some things. If f of a times f of c is negative, that means the root is on the left side. So draw a little picture of what's going on here. Here's a, here's b, and here's c. And I don't want to draw a function because I don't quite know what's going on yet. But if it looks like this or this, the root is on that side. So if a times c, f of a times f of c is negative, that means the root is in AC. We're just going to make that our new bracket, so we reassign the variables. I don't have to change A stays as A. So I'm going to put a little note here, don't change A. But B is now that midpoint. And you could put let here, but this means we're assigning the value that's of C to the B variable. So these A's and B's are just little boxes where we keep things. And our original ones were this, and then for that last problem, we ended up changing that one. So these are just little storage spaces. All right, sorry, it's hard to know what you need to hear, so you'll probably hear me say some things that might seem remedial or weird. Else, we know that this thing changes. So this else meaning f of a times f of c is actually greater than or equal to 0. If that's the case, then don't change C or B and let A now be equal to C. And we now have it.
You wanted to say A equals C.
A equals, thank you, yeah, thank you. And let A equal C. So that, in that case now we're actually on this side over here. This is our new A, and this becomes B again. And we repeat. Now we just go back and we can just feed this to itself over and over again. So, end loop. And that means return to start. And do it again. So let's try to get a stopping condition on here. Labina, what would be a good stopping condition?
Are we assuming that we have a root first?
I'm sorry, friend.
Are we assuming we have a root?
We're assuming we do have a root, yes.
So can we stop if whatever our variable is equals to our root?
But we don't know the root. That's the problem. Hold on, let me check. Vivian had her hand over here.
Oh, no.
Oh no. Okay. Eva. Yeah.
Well, you could do like end value minus initial value equals, find that, and then if it's equal to however error we want, then we're happy to stop.
Perfect. So look at the width of the current interval. If it falls below a specified tolerance that we haven't set up, we'll call that good. Yeah, perfect. So we're going to loop while, and we're going to say here b minus a is less than, and b is always, the way we're doing this, b is always going to be greater than or equal to a. So I think we'll be okay. If you feel safer, never hurts to slap an absolute value on there. While the absolute value is less than our tolerance level that we haven't specified. So we need to go back and add that to the start of the code. So at the code here, we're going to specify tolerance, TOL, equals our max error. And we're going to keep going until these two things are less than that far apart. So for example, let's talk about how I would use this. What if I wanted 5 decimal places of accuracy? If I wanted 5 decimal places of accuracy, I would set tolerance equal to 10 to the -6th. So that in that 6th digit, I can have a little bit of change, but everything before that would remain the same. So this guy here would give 5 decimal places of accuracy in our final answer. Does that sound okay, Lou? Okay, I just like your brows were a touch bit furrowed, so.
No, I was just trying to remember how while loops work, because I couldn't remember if it's while the condition is true or false, because if you want to, right, because we're stopping once it's less than the tolerance.
Yes, so we would do, yeah, I think that if,
False. Okay.
oh,
Couldn't
right,
remember if
thank
it's
you.
while true
Yes,
or
thank you,
false.
sir. Yeah, greater than tolerance, yeah. That's the way to do it. Yeah, we want to keep doing this until we fall under or equal to our tolerance. Thank you.
No.
See, your furrowed brows always contain great information. Thank you.
Sounds well true.
Yeah. Does that make sense? Thank you for catching that. Yeah. Or this could be until, we could do until this, the thing that I had up there happened before. So until this falls under the tolerance. All right, that's it. Let's look at the code and let's play. So, God help me, I've got to get this thing going. Whatever Great Force, Thor, be my steel. Not that Thor. The Thor, not you. But when I think of Thor, I think of Christian. Okay.
One of the HDMI cords isn't plugged in.
Is anything even?
It's like, that one's not plugged
That's
in.
grim.
What is that one? Is it?
Right?
Is it? So this one goes to the computer. So that little fish you just plugged in.
This is the one that I had
Okay.
earlier.
Thank
That's the
you.
one that goes to the
And it goes, oh yeah, that's cool. That's a nice one.
This one's tagged out.
This goes, oh, maybe to a laptop?
Maybe.
Maybe I'll start bringing my laptop. Because now I made the mistake of not turning on a Regis computer 4 hours ahead of needing it. Oh, this is good. Wow, look at this. Let's all go to world class. And we're going to go to the content area. There's a Jupyter file. This might take a few minutes. So find the Jupyter file that says bisection method and bring that up into Jupyter. And if you need help, we're all here together. Gut. Okay. And let's see if I can make this happen. It all sounded pretty good. And we'll go through it together. I mean, if you get it open, feel free to start playing with it. If you see someone who needs help, help them. I'll probably have to do this. Look at that, it worked. That's good, because I've got some really cool shit. It's not the bisection. Anyone having trouble getting that going, getting that opened up and seriously, I just did that. Oh my god, somebody's got, oh, I have MetaMask, oops. Oh shit, it's syncing with my life. I don't think I want that on display randomly. Oh my god. Anybody else here use MetaMask for crypto stuff? You guys, you don't have enough money to do crypto stuff, right? You want to actually be smart with your money and not just piss it into a hole in the ground, a digital hole in the ground. Oh, maybe I misspelled world class. I am super into DeFi gaming. That's like, what's that?
Gotta read just these.
Thanks. No, you're good. I appreciate that. I like got a lot of problems just making it through the day. There we go. All right.
Yeah.
I don't know if I have it set up for the square root of 3. I might have done a cube root. I can't. I'm starting to second guess myself. Oh yeah, don't pay for Python. I don't know. I was just desperate after Vivian told me. I didn't want anybody paying. You indeed.
I don't know what they're like.
Yay! Help! Help! Help!
I got like my
See,
notebook
see down,
open.
so okay.
No,
Down, so
no,
let's
fine.
go.
I wonder if this thing has Python native.
Ah.
Oh,
I know. I was trying to find it. It took me a minute.
Son of a gun.
There you go.
That makes much more sense.
You got it?
Thank you.
Got it? Okay, thank you. Good. Guess I'll have to use the online version. Which you can always find at jupiter.org. You can go to the browser version. Use that freely. Oh, cool. Good. Oh God, no, I'm just gonna dump it in here.
Yeah.
Yay! Wait, that didn't go to the right place. Control C. Let's just go into Jupyter Notebook. Give me a new one. Sure. Okay. This has got a lot of formatting and we'll see if it takes it. Okay, so now I just have to figure out how to freaking get to the file. Oh God, what's the relative path here? Anybody with sense about this stuff? I guess I have to go look at the path setup.
Copy and paste it from the file.
I tried. Maybe I just need to put it as a new one. Yeah, let's try that. So,
I didn't copy the address.
copy the address. Oh, I mean, like here, get the whole path name up here.
Yeah.
Gotcha. Yeah. How do you see the whole path name?
I think
You can like right click it.
Just right click it. Okay.
Like,
I don't know about that. Let's see. Can we copy path here? Just look at properties. Yeah. No. Oh yeah. Users Trenery downloads. Okay. Cool.
you can just copy and paste that code. Just-
Probably could have. Let's try it again. No, I lost it again.
It's like this towards the upper middle.
Oh yeah, thank you. Okay. Let's make that our path. we go. Of course you couldn't.
Get rid of the C.
The C is probably roaching it up, isn't it? But it might, I don't know where the root is, if the root is C, or if the root is somewhere else. Let's try this. Okay. You're right. Yeah, exactly.
I'm out of ideas.
Yeah, me
Can't
too.
you go up in the, right below edit, there's filter files by name.
Oh,
I think you're in the wrong directory.
I think you're right.
You're in the
Oh yeah, yes, yes. Yeah, yeah.
data? I don't know.
Well, let's just find that notebooks folder, and then that'll be the answer.
Where's that?
What's that? You're helping me. So anything you have to say is.
I'm just curious where the.
Half of working with computers is this kind of crap. Ask any CS person.
I have like a big menu when we open up that shows all my files. I'll just go through.
That was nice. Do you use like Linux or something?
No, it's just part of Jupyter Notebook.
Is it?
It's like what it first pops up when I open the app.
Mm-hmm.
I think because you open it from the browser.
I think you're right. I think that is totally right. Well, let's just see if we can plug this in somewhere.
Dr. T, do you
Yes.
want to just run it off my laptop?
Yeah, that sounds
Yeah.
great, Lou. Awesome.
I can
Thanks. Thanks, you're awesome. I guess I'm gonna have to come in here and figure this out, or I think I'll just bring my laptop. Thank you
It
so
should have
much. I appreciate it. Thank you.
I think it's on the other
Other
side.
side, indeed. Thanks, Lou.
I was like, why don't you just take it?
It's taking a while.
I'll just leave it. Woo! That's noisy. Okay.
Let's change the HDMI input of the machine.
Yes. Yay! Oh my God, Lou, you did it.
How the GX does.
Fantastic, beautiful. Thank you so much. So, who has not yet run anything off Jupyter? Who has not? Yeah, couple folks. It's all good, and you should come by, and we can work on some stuff. So, if you are taking notes, I've got better notes here for you. But it's basically, if you look at number one, it's what the bisection method is. That should be in LaTeX. For some reason, it's not. That is in LaTeX. I don't know why it's not typesetting, but it. What's that?
Not formatting or
Yeah, that should look really beautiful.
maybe you can just.
Mine does.
Yours does?
Yeah.
Mine doesn't.
I don't
Cool.
know why Lucy's
Maybe just
I think
format
it's
it.
so it's a
Get
touchscreen.
run.
I think you clicked into it. Like
That makes sense. That
Yeah.
sounds like something I'd do.
So mine was pretty after I like
Yeah.
ran the pause, even though it didn't do anything.
What's that, Thomas?
Or after I just like clicked run a bunch of times, it looked pretty after that.
Okay,
So-
okay, cool. Let's just give it some, we don't even care. Basically, it's got all the stuff we already talked about. It's got our pseudocode. Here's slightly better pseudocode right here. And here's the real code. So everything you do in this class is going to start with an import numpy. I like numpy better, but it probably numpy makes sense. That's numerical Python routines that are going to be at the heart of everything we do. If you're not used to functional definition, I'm just going to go through this. Notice I say define f of x, colon, and then the return. This is what the equal. This is equivalent to equal. Remember that exponentiation in Python is 2 stars. It's not a caret. The caret is a bit operation. So this is what we want, but I don't actually want that. I want the square root of 3. So if I wanted the square root of 3, or square root of 2, I would change that to squared minus 2. And so now at this point, I'm about ready to find the square root of 2 if I just run this method. So let's look at what our tolerance is in our initial bracket. Is this a good bracket? Yeah, it's a pretty good bracket, right? It's better than our first one. It's actually that second bracket we came to after narrowing things down. So you make a good estimate here. Don't get crazy, let the computer do the work. I'm setting the tolerance to e to the -5 so that I get 4 decimal places of accuracy. I'm also setting some max iterations here so that this thing doesn't run forever. And we'll talk about how run forever could possibly happen in just a little bit. So let's see what this gets us. And let's actually, I'm gonna actually say 1,000. Come on, we make the computer do the work, right? And then you go up, you click in the routine you want, and you hit play, and it's done. It's already done. So we've got, let's see, the root is approximately 1.414. Oh, I was doing square root of 3, wasn't I? No wonder that's wrong. Sorry. Change that to a 3. That's easy. Play again. 1.7320. And that's about all the accuracy, because I'm pretty sure the next one is a 5. But it rounds up to a 5, so we're doing pretty good. We do have 4 decimal places of accuracy right there. Let's run it a little bit more. Computers are so freaking awesome. What if I wanted 10 decimal places of accuracy? Let's try that. So I just adjust the limit. And now we've got a pretty damn good square root of 3. If you want to do things like this in Python, you can just go to a line. So for example, I can just, underneath this, I could just say, I think it's sqrt3. Does that sound right?
Yeah.
Yeah. sqrt3. And that should just print it. Let's see.
I think you have to put it in a print.
Yeah, I guess I do. Oh, I guess because the other stuff's there, I can't use it in calculator mode. So get out of your way.
Square doesn't
Yeah, so let's say print, and I'm going to do the laziest print possible.
Oh, don't you have to also pull it from numpy?
Yeah, so I can just
Yeah.
say np dot square root. So check this out. So all this was good stuff to watch, especially if it's been a while or it's been never. We need to access the routine square root, which is in the numpy routine. So notice I imported numpy as np. That means anytime I refer to np, the computer knows I want something from numpy. So from the np package, grab square root and find the square root of 3 and print that mofo. And there we go. So now we actually see we've got really good. I don't even know. This stuff out here isn't good, but we could make it good by lowering the tolerance. And this is super fast too. This routine is incredibly fast. Is everything okay, Libby? Nothing working okay?
Oh no, I can see like.
Well, it's good you sat in the back.
It's like really hard to see.
We'll get you like some opera spectacles or something. Small telescope. Do you, I don't know how to make it bigger, honestly.
I think it no.
Oh.
That works.
And then, of course, now you can't see anything. Let me undo that. I'm sure there's a font I can change here, but I'm not gonna F around with it. So this is stuff you can play with. Honestly, I just put a bunch of stuff in here so you would have examples of the kind of code I'm gonna ask you for. And Christian, you can like take this and spend some time with it, playing with it. That's the way to learn how to code, is take some code and play with it. Because I'll never ask you to do code from scratch. So never stress about that. Now look what I made down here. You may not be familiar with matplotlib. Who's been used matplotlib? Probably physics folk, probably, yeah. So not everybody. Matplotlib is a mathematics plotting library. And it allows you to create really nice graphs, but it's not the most user-friendly thing. It's really old school computer descriptions of things. So the first thing I'm doing here is I'm creating an array of numbers from 1 less than our left endpoint to 1 more than our right endpoint, and I'm cutting it into 400 equal pieces. So this creates an array filled with all the samplings 400 times between your left endpoint and your right endpoint. because we're gonna do a plot, so we need to have some x values to spit out for y values, and we need a lot of them so it doesn't look all jagged and polygonal. And then y is just our function that we've already defined above. I'm not gonna go through every little bit of this, but it would be worth your time to play with this, because I will ask you to produce plots. When I ask you to produce a plot, take this and hack it. That's literally, like when I was at IBM, I was just like, I didn't know how to, I had no freaking clue. I'd taken one C course because I had just been hired at IBM. I was like, shit, I better know something, I guess. So I got there and like, I was just like constantly trying to keep my head above water. Quite a painful experience. So let's run this thing. Come on. Is it run? No, I don't think I ran it. Why is it not running? I don't even see it. Oh, there it is. It just took, it's just slow.
Matplotlib takes a while.
It does, yeah, you're right. So this is our scenario here. You've got a graph, here's your x-axis, here's the square root of 3, and here's the initial interval with the between the red and the blue, and then the midpoint is at the green. Just showing you kind of what's up. You wouldn't want to print that for every single one. And that's just the same code. Let's see, did I tweak this? What's this one do?
Those are the number of iterations.
Yeah, oh, yeah. So that is nice. Let's take a look at that. And then let's see if we can predict, match its answer with math. Why is the midpoint of it not running?
I think it's above. That looks not. Yeah.
It's this code. Oh, right, that's the markup. Okay. So 32 iterations to get, how many decimal places of accuracy did I request? What was my, do I have my tolerance printed out there? Yeah, 10. For 10 decimal places of accuracy, 32 times we had to have things. Let's talk about that mathematically. I'm going to turn this off for a second. At great peril. I might need that again, Lou. Let's just shove it against the wall and make it look at the wall for a second. Okay, good, because I'm not turning it off. Wow. Very bright, very distracting. Made me think of that very demure thing. God. Okay. So let's talk about number of iterations. And it's something you want to keep track of. So one of the big problems in doing math on a computer is time. Time is the utmost importance for these algorithms, because we want them as fast as possible and we want to understand how long they can run. One of the things I did at IBM when I first got there, my first job was to take image processing code and make it faster, which was super easy for a guy who had just taken his first C course. It was like, oh my God, I had to learn so much. Every day was college and stressful until I stopped giving a shit. And then I came here and started giving a shit again. So how many iterations? This is a question I have for you, and I'd like you to just take a minute. Do we need to get b minus a? We'll just say, we'll assume b is always greater than a, less than some epsilon. Can you take a minute and just think about this? To get, yeah, that's exactly what I want. So think of this as the current bracket. Let's do a little thinking. How are we going to approach this problem? This is now math. Now we're just doing math. And remember how the process works. We cut it in half every time. So think in terms of stages. So here's I'll just get you started. Original length is b minus a. After one iteration, first one iter, we've got b minus a over 2. Second iteration, b minus a over what? 4, which is, since we're keeping track of things, we're going to use exponents to look for rhythms that are hiding. If I put 4 there, it might hide the fact that the exponent here matches the iteration. The exponent here matches the iteration. So I'll get you even going. The nth iteration, the interval will be this long. Now, let's go back to basics like pre-calc. It's a pre-calc problem. Find n so that this quantity is less than epsilon. Can you do that for me? It's not something you do a lot of, and so I thought it's good to talk about this for sure. You got something, Courtney? Or are you thinking?
What's your epsilon value?
Yeah, so unknown, so let's just make epsilon as some positive number. I don't quite know. So our final answer will be n in terms of epsilon.
So
Yeah.
n has got to be pretty big then, doesn't it?
Absolutely. Yeah.
Like,
How big?
Would you say infinity big?
No, I wouldn't. We want a number, because definitely infinity's going to work.
Yeah.
What does infinity mean to a computer?
Like as big as you can.
Yeah, exactly. So we could do that, but remember that's also the number of times we're going to run this code, and everything that costs. There's a cost associated. So we want to minimize. We want the least number that get us there. But you're right, infinity would work. Can somebody help me solve this inequality?
2 to the 32.
What's that?
Just throwing out
Oh,
numbers.
okay, all right, enough calling out numbers. Wait, Labine, is that a hand? Okay, Lou.
So I want to I worked it out, I think, and it's like n has to be greater than log base 2 of b minus a over epsilon.
Yeah, that sounds right. Let's get there. Let's get there together. So first things first, I won't make Luke teach us this. I'm going to multiply both sides by 2 to the n and divide by epsilon. And already it's starting to look a little bit better, because now at least n is on one side. I've got the n not quite isolated, but it's over there. And then to get this down, you're going to take a log. You can take any logarithm you want. Let's just take natural log. So I'm going to take the natural log of the left side. And I'm going to take the natural log of the right side. Why does inequality get preserved? How do I know that if I take the log of that it's still less than in this way? How do we know that?
Signs haven't changed.
True. How does that relate to natural log?
Can't have natural log of negative number.
This is true, definitely. These were both positive. So the way we set everything up, we're pretty good here. We're positive and positive, because epsilon was positive. Why is this true? I mean, this is math. It's pure math now. What does a natural log graph look like? Looks like that. It's an increasing function, so that if I move to the right, the output value goes up. So it preserves order in a way. So I had to know that natural log is an increasing function, all log. So I'm going to put a little note here, because ln is increasing. Because it's certainly not always true right? What if I had f of x is 1 over x? And then I know that 1 is less than 2, but f of 1, if that's f, is not less than f of 2. In fact, the inequality flips. So you got to just be careful about your functions when you're working with inequalities. You need to know something about them. So now we got this, and so this side, I'm going to pull the n out in front. That's why Lou took a log. Pull that n out, and now that's just a constant, and we divide by it, and we're good to go. So 1 over natural log of 2, natural log, epsilon. So n has to be greater than this number here. So let's take a look. Our epsilon was, what was it? Was it 10 to the negative 10th? Is that what I set it to? Yeah. So let's put 10 to the negative 10th in here and crank this through. Let's use b equals 1, b equals 2, a equals 1, which makes a nice 1 on top there. So here on this left side, I'm going to get 1 over natural log of 2 times natural log of 1 over 10 to the negative 10th. And I know that n has to be greater than that. So what's this guy here? That's 10 to the 10th. We can pull the 10 out in front. I think I did that okay. Yeah, could someone crank that out on a calculator, please? I mean, I could. I will. Phone out, see if I can beat you. Left my damn phone home. No, I left my phone right here. What'd you get? 33.
33 and some change.
33 and some change. Awesome. So this is approximately 33 and some change. So we want 34 iterations. How many did we have? 32. It was 32. This is good. This would definitely get us to that precision. 32 maybe got us there because of some subtleties in the function itself. But if we had 34 or more, we get our desired accuracy. Cool. So I've only got like 7 minutes left. This is going to go a little bit faster if you get the reading done ahead. We don't have to go through every little detail. We can kind of talk about things more. But there's something that's coming up that you will read about that is one of my favorite things in math. It's really sad that I only have 7 minutes to talk about it. But we're going to talk about iterative methods. So recursive methods, let me think of it that way, say it that way. Because this is an iterative method, but it's not recursive. So what we're going to do is we're going to look at solution methods that look like this. Some process x sub n. And our x sub n is going to be an approximate solution that hopefully gets better with time. That is our goal, and it won't always be that way. One of the things you can think of this as, and this is the part I want to really just talk about a little bit. So, oh, do me a favor. You got calculators? Go to the calculator, make sure it's in radian mode. Hit cosine of 1. So hit 1 and then cosine. What do you get?
I've got
0.54, something like that. Now take the cosine of that.
Cosine of cosine of 1.
Cosine of the cosine of 1. And keep doing that for a while, would you? Just keep taking the cosine of the output.
0.857 for cosine of 1.
Yeah, keep on going. Watch the output. What is happening there?
Stabilizing.
It's increasing. It's decrease. Yeah.
It's going up and down.
It's going up and down. Keep going.
It's stabilized.
Does it stabilize? Yes. How many times do you have to do it to get the first digit to stabilize? It's not that many, is it?
I don't know, I just kept going, I was like.
Okay, all right, don't fucking worry about it. All right. So you do this a bunch. What is it settling down on?
Points.
0.7 something, right? 0.7 blah, something. But it settles down. So if I have this cosine of the cosine of the cosine of the cosine, etc., it eventually settles down to this number. So let's think, this is actually what we're doing here is a system that looks like this. We're doing an iterative scheme where the next value is the cosine of the previous value, and we initialize the process with a 1. So x sub 0 is 1, x sub 1 is the cosine of x sub 0, which is 1, and then I just repeat this over and over again. So I loop here. Here's what's happening. And when you see it in graphical form, it makes all the sense in the world. Here's a good old cosine of x curve. So here's my y-axis, here's my x-axis. Here is y equals x. Here's what you were doing. You were picking one. Let's see, this is, what's that value right there, the exact value? Oh yes, thank you. Yay, I can go on through the day happy. So that's pi over 2, that's like 1.7. This isn't great, but we'll say that's 1 is about right here. So yeah, this is approximately 1.7. This is good. This picture looks like shit, quite frankly, in terms of scale. But what happened was we took the cosine of 1, which is this output value right here. This is cosine of 1. And then we fed that back in and took the cosine of it. So to find the cosine of 1, I flip this value over the diagonal, come down and plug that into cosine. So the way this picture looks, it would be this, but my picture's pretty bad, so let me fix it really quick. Actually, let me just show you. And this is the last thing I'll show you. Let me get onto Lou's thing here, and do you mind if I search Lou?
Oh, go for it.
All right. I don't know if you use Google as your default, but I'm moving to it. So let's do cobweb.
My data's
Interactive.
Your search is cool. Search suggestions.
Yeah, I didn't look. I wasn't looking at what those might be. So let's enter our function here. Our function is cosine. Oh, do I have to wait for it to come to life? My goodness. So let's do cosine of x. I'll let you out in just a second. Hit enter. Ah, that is a much better picture. So we're going to set our initial x to 1. Oh,
Can't see it.
yeah, thanks. Yeah, thanks for the tip.
Now you can.
Give it a little bit.
Okay, how about that? That keeps us all fresh and awake, doesn't it, my crazy antics? All right, so we're going to set x0 to 1. I'm going to hit enter. So now I can iterate through this. So x of cosine of 1 is that value. We flip it over the diagonal, which is essentially moving horizontal to the diagonal and then back up to the curve. So this is called cobwebbing, and it's literally what you were just doing. It's very slow, but it's honing in on our actual solution. What am I solving here? Notice how it's settling down into that beautiful spiral. This is why it was going up and down as well, because it was spiraling in on the value. What did we actually just solve here? We solved this equation. cosine of x equals x. So we found the root of cosine of x minus x equals 0. And it's that number. So this method, you're going to get a chance to read about it. I've got a really cool story to show you, but we're out of time. It's got cool colored pictures and voyages into inner space and stuff, but we'll get there next week. Thanks, everybody. So your only homework now is keep an eye on your email so I can find some Python shit and read.
You want homework 1?
Yeah, so homework 1, if you didn't turn it in the Dropbox, I'll take it now.
Is there still time to go to Sarah's middle
Well, it was, we can. We would try to do that before the due date in general. Yeah, but yeah, you can come back.
Is it due today or due like in the Dropbox?
I think that's.
No, if you already turned it in, I'm good.
I stamp it, but I put my name and the page number.
I know your handwriting.
I'd like to do it.
Yeah, it wasn't.
Sounds like the CS department is gonna work to help us out here on this
Yeah.
situation.
No, I think it's all good. I think it's actually good. 'Cause I think they, well, okay, I think, I don't know.